Well, I never expected to be quoted in the Financial Times, but such were the exceptional sea surface temperatures during 2023 that news of them reached even that newspaper, and so I ended up being interviewed. This talk is about those exceptional SSTs and begins to answer what has caused them. So let's look at the data first. This is a plot of a number of years of global SST between 60 north and 60 south against time of year. And all the SST data in this talk come from the ESA Climate Change Project. The grey lines here are the 1980s, and then I've plotted 1991 in red. And to emphasise when a record is broken, where 1991 exceeds any previous temperature in this data record, I've dropped a colour down from the red line to fill in that gap. And it just shows us immediately where records are being broken. Now, let's run the data forward year by year through to the current time. And what we can see is that there tend to be years that break global sea surface temperature records by a significant degree, and then runs of years where that doesn't happen so much. Now, the years where a big step change in global SST occur are the El Nino years, when the ENSO, the El Nino Southern Oscillation, is in a positive phase. And notably, we see this happening in 1998/9 and in 2015/2016, and of course in the past year. But what's quite obvious is that even amongst those record-breaking ENSO years, 2023 and 2024 were quite exceptional in the degree to which global SST records were broken. So on the left here we have the same data just presented as a normal time series, and you can see the annual variability. There's a bit of a trend and some of the interannual variability as well. To make things clearer, let's deseasonalize that by removing the long-term climatology, which is shown on the right. And we end up with this deseasonalized global SST, which makes the trend somewhat clearer and also shows more clearly the variability, including the variability in those ENSO years. Now, the fact that we can see the big El Nino events in 1998, 2015 and in 2023 gives us a clue that we can actually represent quite a lot of this variability with relatively few factors. So one of those factors, of course, has to be the El Nino phase, and the El Nino 3.4 anomaly is shown in the top plot here. And we can see that actually the 2023-2024 El Nino has not been by any means the strongest event. Now, below are a number of components that explain a lot of the global SST time series. So we discussed El Nino, and the contribution that El Nino makes to the global SST is shown in the orange line here. But I've also fitted three other factors. There's a long-term linear trend, which represents the effect of the forcing from greenhouse gases. It's also the case that the solar cycle has an effect because the sun emits more radiance when there are lots of sunspots, and so that's being fitted in the red line. And the time series of stratospheric aerosol depth has been used with a bit of a lag to fit the volcanic impacts. Now, if we add those four terms together, we get the orange line in the top plot here. Now, the data have all been fitted for the period up to and including 2015. So the data are only fitted through to the point where there's a dashed dot vertical line. And over that period you can see that the orange line does indeed capture quite a lot of the overall global SST variability. I've also extrapolated that orange line using the same regression coefficients beyond 2015, and that you see at the right hand side of the plot that beyond that date the orange line tends to begin to underestimate the global SST compared to what's actually been observed. Now, the lower plot shows the residuals, the differences between those two lines, the orange line and the observations. Now, of course, during the period up to 2015, there's no trend in those residuals because we've already fitted a linear trend. But to better explain what happens after 2015, we need an additional trend to fit the residuals on the right-hand side of that lower plot. And that additional trend is quite significant. It's an extra 0.2 Kelvin per decade to be able to explain better what's happened since 2016. So let's try to do a temperature budget for the recent El Nino period compared to the 2015-16 event. I'm using an extended winter period from November through to March, and during that time the impact of NCEO is at its largest. Now, the difference in temperature for that period in the past year compared to 2015-16 is 0.22 Kelvin. Now let's see how that could be explained. Well, if we think about the continuation of the same linear trend that we originally fitted, that makes a contribution, plus 0.08 Kelvin of that 0.22 total. Because actually the recent El Nino was not as extreme as the one in 2015-16, the global effect of NCEO is a negative contribution. The solar cycle of irradiance adds a bit, and I've also included from the literature someone's estimate of the warming impact of the Hunga Tonga Hunga Hapai volcanic eruption, which included both stratospheric aerosol, which tends to cool, but also injected a lot of water vapor, which tends to be a warming effect. So if we combine all those explained effects, they add up to plus 0.09 Kelvin, far short of the 0.22 that's been observed. Now, of course, we've only used 4 factors to explain the time series, and there is an unfitted variance here, which we don't know which sign will be for the recent months. And we can quantify that unfitted variance in a 5-month average SST, and it's plus or minus 0.06 Kelvin. So that means that to explain the recent November to March period, we need an additional warming beyond those 4 factors of 0.13 Kelvin, with some uncertainty on that of 0.06 Kelvin. And that corresponds to an extra trend of 0.16 Kelvin per decade, very similar to the estimate we found by fitting the residuals in the previous slide. So, is there an acceleration in the SST trend? Well, let's think about what a long-term linear trend in SST corresponds to. It would be what we get if we have a stable Earth energy imbalance. So after the climate system has adjusted to the effects of greenhouse gases, there is an imbalance in the energy coming in to the Earth from the energy that's leaving the Earth, a radiation at the top of the atmosphere. If both that Earth energy imbalance is stable over the long run, and that energy is being distributed stably across different components of the climate system, then we expect a long-term linear trend in SST at a constant rate. And what we're assuming here is essentially that the fraction of the Earth energy balance that goes into the ocean mix layer is constant over time. And that will give us a long-term linear trend. If, on the other hand, an upward step in the EEI occurred, that could accelerate SST above the previous trend. And that's possible because in the past decade, greenhouse gas concentrations have increased, and particularly methane has increased faster than had been the previous trend. And at the same time, anthropogenic aerosols over the oceans have decreased. That's because of cleaning up factories, but also because of the cleaning up of sulfur in marine fuel for shipping. And decreasing anthropogenic aerosols allows more sunlight to reach the oceans, as well as having impacts on clouds. So has there been a change in the top of atmosphere energy budget? So I'm showing series data here from NASA. On the left is the raw data, the net all-sky radiation. So this is all radiation streams, infrared and shortwave, in and out, and their net when you add them all together. That's obviously got a strong annual cycle, so again I've deseasonalized those data and show that graph on the right, which makes clear what's been happening. So we have monthly deseasonalized data in green, and then annual averages for years that run from March to February each year. And that's in the orange line. And you can see that they do suggest that there has been something of an uptick in the EEI. So I calculated the mean Earth energy imbalance for the period up to the start of 2016, and then for the period from 2016 onwards. And those levels are shown in the dashed red lines. And you can see that from 2016 onwards, that mean is plus 0.63 watts per square meter greater than the previous period. Now, is that flux, that change in EEI, enough in principle to explain the SST trend that we've seen, the additional trend? Well, the mean mixed layer depth of the ocean is about 63 meters. And with a mixed layer of that depth, if you put all of the 0.63 watts per square meter into the mean mixed layer, that could heat the mixed layer at 0.73 Kelvin per decade. So that's plenty, that's much bigger than the additional warming that we've seen. Now, if we also account for the fact that the ocean doesn't cover the whole of the Earth, it turns out we need only 25% of the additional Earth energy imbalance to accumulate in the mixed layer of the ocean to deliver those recent record SSTs. But is that plausible? Well, another way to look at it is to do the calculation assuming a stable distribution of energy around the system. The ratio of the mean Earth energy imbalance before and after 2016, or I should say after to before 2016, is 1.7. So it's increased 70% in the mean from 2016 onwards. Now, if the heat is being distributed easily, we'll have the same ratio in the trend in SST. So the trend in SST pre-2016 was 0.11 Kelvin per decade. So with this stable distribution assumption of the energy across the climate system, this would imply an additional 0.08 Kelvin per decade of SST trend since 2016. And that's half of the additional SST we see for 2023 and 24. So this effect can be the attribution of about half of that uptick in warming. So let's wrap all that up into a conclusion. The exceptional SSTs of the last year can be budgeted as follows: 40% from the usual effects that we've seen in previous decades, 30% from the increase in Earth energy imbalance since the last or during the last ENCEO cycle, assuming that that imbalance is stably distributed around the climate system, and then 30% from other factors. There are some implications of this. If the Earth energy imbalance uptick were to prove long-lasting, then the new normal SST trend will be around about 0.18 Kelvin per decade, rather than the 0.11 Kelvin per decade that we've been used to for 40 years. And it's a key question here is to understand whether in those other factors we have factors of variability which will dissipate away, or whether there might be any systematic or persistent aspect, including perhaps a change in how the Earth energy imbalance is distributed in the climate system, which could be more persistent, because that would also affect the future trend. So the implications are quite important, and we need to try to understand better the other factors that have contributed to the exceptional SSTs of the past year.